So welcome to the 23rd Physics Matter Forum. So this series, Physics for Development, has been initiated during the COVID time, so by Luisa Cifarelli that you see here. And it had permitted us to visit, in kind of a virtual way, but to visit and travel around the globe, proposing a broad popular scientific topic related to applied physics and the Sesame project, but mainly connecting developing and developed community around exciting topic. So last month, live from Jerusalem, Professor Rabinovich had recalled the fascinating tales of the Sesame as a source of light in the Middle East. So we are delighted as well that this physics matter had even triggered some additional support for this international effort. So let's see how in this coming forums, we are also opening new gates for more challenging, so the so-called challenge-based innovation. So first of all, I want to apologize for the change in the program that we had as our original guest. So the speaker who was supposed to be Professor Bernard Amadei, the founding president of Engineers Without Frontiers, has been asked to leave, and he had to go to a field trip to Uganda, so he didn't have any access to the internet. So we will keep this mystery around the topic that he will propose in June. So how to navigate the complexity across the peace, sustainability, climate. So, but more of all is that in the middle of difficulty, we know that we can find opportunities. So we are thrilled to welcome Nicolas Delerue today for our special Physics Matter platform. And we will introduce how the environmental and the educational topic also can be, who are also precious to Bernard Amadei, could also be seen from that other angle. So using particle accelerator. So, and with this similar topic of multidisciplinarity. So this is an approach which is important to us. So as a member of our panel today, so we have Luisa Cifarelli, from Bologna University, who is the past chair of the Forum of International Physics. And I will list all the different speakers. My name is Christine Darve. I'm coming from the European Spallation Source in Sweden. Nicolas Delerue, he has been obtaining his PhD, in mathematics, physics, and particle physics with honor at the University of Mediterranean on topic related to electron-proton collider in DESY. So this is the HERA Accelerator in Hamburg. So Nicolas is a fellow of the High Energy Accelerator Research Organization at KK, in Japan, in Kusubi. That was from 2002 to 2004. He's lectured at Oxford University until 2010. And since then, he's a senior beam physicist in Orsay, the laboratoire des accélérateurs, de l'accélérateur linéaire, le LAL. In parallel to his duty, he's also coordinating this challenge-based innovation, Accelerator for the environment. And this is for the innovation fostering at Accelerator Science and Technology, the I.FAST, which is an Horizon 2020 program, Research Innovation Action Program. So in our panel today, we have also the honor to have with us, Rema Altamini, who is also from the I.FAST, this CBI, former student of Nicolas. So Rema is a second-year master student, in Science and Communication, of Communication and Information at the French Press Institute in Paris 2, the University of Paris 2. So currently, she has her second year of master's, and she specialized in media studies with an extra focus on political and social science. So she's passionate by communication and popularizing science, and she's doing her master thesis on science communication as a tool to challenge conceptually the theory around science. Sorry for that. So taking the case of CERN, in which she had 3 months internship before. So Messoud Arafo has a PhD as well. He's currently a senior beamline scientist at the BMO8. So this is the beamline in the Sesame in Jordani. In 2003, so Dr. Afours obtained his PhD in geomaterials, so from the University of Marne-la-Vallée in France. He joined the PSI Institute as a postdoc fellow, so at the Nuclear Energy and Safety Department, before becoming a beamline scientist for the Super XAS beamline at the PSI department in the Swiss Light Source department. So as a beamline scientist, so he has dealt with many research domains in order to support users from various fields. And his personal research interests focus on the air pollution, the soil contamination, and the nuclear waste storage. That will be a bit more open as well towards now more, environmental challenge with the last speaker who in the forum part, so we'll discuss from the ESCAT, so another research infrastructure in Sweden. So with Judah Veridner, so he is currently an associate professor of the space physics at the University of Tromsø in Norway. So he obtained his doctorate in 2012 from Helsinki, so in the University of Technology, on novel model for using powerful radar to remotely sense the Earth's ionosphere. So this is so in 2013. So when he joined the MIT, the Hestat Observatory as a postdoctoral associate, and in 2014 as a research scientist. So in 2016, he joined the University of Tromsø. So his main research topic now is the use of radiofrequency electromagnetic wave to study the Earth's ionized upper atmosphere. So you see that we have a very interesting panel that we will reconnect after the presentation of Nicolas Delerue. So we will invite you, so during the presentation of Nicolas, to prepare your question and answer. So you have a raised hand, but maybe if you want to write them and prepare them, you have the question and answer session where you can prepare, and after the presentation of Nicolas, so we can come back to your own question before we start the forum. So then I let you the screen, Nicolas, if you want to share your screen.
Thank you. Thank you, Christine. Thank you for the very nice introduction. Oops, sorry. It was, yes. Okay, do you see my screen in full screen?
Yeah, that all works.
Okay, so I am going to talk about the I.FAST challenge-based innovation. It's a challenge that took place last summer and that is going to take place again next summer. So first of all, what is I.FAST? I.FAST stands for Innovation Fostering in Accelerator Science and Technology. It's a European-funded project. Here you have the website. It involves 49 partners, mostly research organizations, but also a few industrial partners. And it includes all big players in accelerator science in Europe. So CERN, obviously, CNRS in France, the University of Oxford, and several other UK universities, INFN in Italy, DESI, GSI in Germany, and also some smaller partners. Of course, ESS in Sweden also. It's gathering top researchers in the field of particle accelerators, and its goal is to look at innovative application of accelerator technology. Oops. European projects are very important in the accelerator community in Europe. Basically, the aim of this project was to create a well-integrated community, and it worked rather well. Over the past 20 years, there has been several European Union-funded projects gathering researchers from all across Europe. Here you have the name of them: TIARA, EUCARD, ARIES, I.FAST. And the aim of this project is to encourage institutes to work together on a given topic, even across countries and so on. So, for example, in I.FAST, there is a collaboration in ultra-low emittance storage ring. There is a collaboration on superconducting magnets, a collaboration on novel particle accelerator concept also called laser plasma acceleration, and on the development of additive manufacturing of accelerator components. This collaboration tried to also strongly involve industrial partners. During the previous project, ARIES, there was a MOOC that was established and that is used now as introduction for several schools. So, and now what is the I.FAST challenge-based innovation? So it's a concept that was proposed a few years ago and that we tried last summer. So during 10 days, 4 teams of 6 students tried to suggest innovative solutions based on accelerator technology to address a given challenge. And on the last day, they present their work in front of a jury at CERN. So last year, the aim of the challenge was accelerators for the environment. So can you suggest innovative use of accelerator technology to address this challenge about accelerators for the environment? So the way we decided this topic was to look at the Horizon Europe mission. So your Horizon Europe is a European Union program that has some priorities, which are listed here: cancer, adaptation to climate change, including societal transformation, healthy oceans, sea coastal and inland waters, climate neutral and smart cities, soil health and food. And the list of these missions is given on the website here on the slide. So we gathered a program committee and we asked them to look at this different mission and to suggest a topic for the I.FAST CBI 2022. And you have the list of the members here, and this included Christine, who is present today. After we selected Accelerator for the Environment, which cover both the maritime and environmental, so the maritime environment and the terrestrial environment, we decided to keep the same topic for 2023, and we will soon gather the expert panel to select a new topic for 2024. So, who is taking part in the CBI? Our target audience is students sufficiently advanced in their studies, but not yet too specialized. So we decided that the best target would be students in their second cycle of studies, which is typically in Europe, 3rd to 5th year of university, and before the start of doctoral studies. But we did not close it to younger students or to elder students. So we selected 24 students, and we decided to have multidisciplinary teams. And when we advertise the challenge, we really look to have students coming from a different background. And for the selected students, all expenses, including travel, are covered by the project. So last year, we got 187 applications. 85% of them were affiliated with universities in I.FAST participant countries. And if we look at the gender balance, we got 57% male, 40% female, and 6% who did not answer. This is an interesting plot. It's the day versus the number of applications we got. And last year, it was very interesting because we had a steady increase of application. Then we had set a first deadline on the 14th of February, and we got more applications for a few days. But because in some fields we did not have enough application, we extended the deadline. We got again an increase and then a sharp rise before the final deadline. This year, the pattern is slightly different. It started faster, and then the slope has been lower. And recently, we have moved into an exponential increase, but we still have only 50 applications approximately. We would like to reach 100, and the deadline is in 1 week. So where did the 187 applications come from? So if we look at field of studies, 39% of the applicants were from engineering, 37% from physics, 11% from environmental science, and then 9 applications were from other fields of scientific fields, 6 were from law, 5 from management and business, 3 from humanities, and 2 from medicine. So if this gives a very different selection rates, in physics and engineering, we selected only 8.5% of the applicants. In environmental sciences, 20%, and in the other field, also about 20%. Yes, and I already give you the gender balance. So for us, diversity is a key to foster innovation. So we wanted to have diversity in many different ways. So diversity of country of study, diversity of gender. At the end, we had 12 male, 11 female, and 1 who did not disclose his gender. Diversity of studies, and we selected 7 fields: physics, engineering, environmental science, law, business, and communication. And at the end, in each team, we had for students who had already extended expertise in accelerators, for physicists not expert in accelerators, for engineers not expert in accelerators, for environmental scientists, for lawyers, and for students from other fields. If we look at the universities of the students, they were located in 13 different I.FAST countries. And if we look at the citizenship, we had 17 different citizenship, including some from outside Europe, like one student from Colombia, one student who is present today, Rima, from Palestinian territories, and a few other countries outside Europe. That I already mentioned. The challenge took place at ESI, which is the European Scientific Institute. You have a picture of ESI. It's just next to the border between France and Switzerland. So Switzerland is here. CERN is very far in the background, and ESI, the European Scientific Institute, is here. So it's very convenient to go to CERN and to other facilities in the Geneva area. ESI has a very strong experience in hosting scientific schools. For example, they host the Joint Universities Accelerator School, which is one of the main schools for university students in accelerators in Europe. Here you can see, for example, a picture of one of their lecture theater. And the ESI team is taking care of the logistic, full board accommodation, and travel arrangement for the participants. So basically, for us as organizer, it was very convenient to be able to give all this to the ESI team. And for the student, I think it was also good because they got help with their travel and all the arrangements. So the program is aimed at giving the students the opportunity to learn about accelerators and their application. So before they come to ESI, there are online seminars. So 4 online seminars before the challenge, plus some video sessions to get to know each other, first all together and then by team. And then last year, there were 8 in-person seminars with experts of accelerators and other environmental applications. They spent 2 days at CERN, and we also had 2 special days that we called conferences. I will come back to it later. So this is to give you an idea of the program. It started on Tuesday, 26 July, with some seminars. The next day, we went to CERN. The following day, we were again at seminars. Then we had what we call the first conference. And then on the Saturday, we again had some work for the students. On the Sunday, it was a relaxed day because they went to Annecy. And the following week, on Monday, there was a seminar. The second day, the Tuesday, was the second conference. Then there was one more day for work, with also a deadline to submit reports for the jury. And the last day were final presentation at CERN and then an award ceremony. Here you have the list of speakers for the online seminars. So it's experts in accelerators, both general accelerators and also some experts in smaller accelerators, more focused towards the application. And we also had Christophe Goupil, who spoke about a physicist's journey through the ecological transition to explain a bit the idea of transition. And then we invited 8 speakers, and you have their name here, to the ESI to speak with the students. It's very important for us to have speakers who come to ESI because like this, they can interact with the student, and we find it's much more interesting. Last year, it was a bit of a challenge because we were still in COVID time. So when we started to organize it, we were locked down, or at least we are not really able to travel. It was complicated. So for a very long time, for example, we were not sure that we would be able to have the challenge in person or to have the speakers come. One of the students tested positive a few days before coming to ESI, so we had to cancel. So at the end, there were only 23 students present. For other students who canceled, I was able to replace them, but 3 days before it was too late. And almost all speakers managed to come to ESI and to give their presentation. So at the end of the COVID time, it was a relief for us. And it was very, very pleasant to meet people again directly and not through screens. This is a picture from the visit at CERN. So this is a dipole from CERN. And basically, the student had the opportunity to visit 4 accelerators, Yelena and the antiproton decelerator, LINAC 4, Cloud, and Clear, or the cyclosynchrotron, depending on their preferences. Those are pictured during the visit. Then a very big structuring event for us was what we called conferences, or pitching event. So twice during the challenge, we gathered all the participants and we asked them to speak to all the other students, both on what they knew and also on their project. So the first one is an opportunity for each participant to present the problem given, Accelerator for the event, from the perspective of his or her field of study. And like this, they can learn from each other, from different fields, also from different backgrounds, even in the same field, how they see the problem. And then at the end of the first day, they also present a bit by team the project on which they will be working. And the second one is more focused on the solution proposed to the challenge. And each team gives a presentation, and then we encourage the other team to give constructive comments from the on the solution proposed. And something that was very important for us was that we wanted a constructive collaboration rather than competition between the teams. And my feeling, but we can listen to what Rima thinks, is that it worked rather well. All the teams were asking questions on each other and helping each other, I think. And that's a bit because coming from the Accelerator community, it's a community where each institute has its own facility and tries to do the best, but also we collaborate and try to make many developments together and help each other. And when one facility is starting, people from other facilities come to help. And that's what we are trying to emulate during the challenge. We decided that we let the team decide how they organize themselves on their own. And I was going to speak with all the teams, and I saw that we had 4 different teams with 4 very different organizations. Some were very democratic, and very often they were voting on what they would be doing or something like that. Some others followed the leader. Some, I would say most, at some point had a disagreement internally, but it's exactly like in a real scientific project. And even when there were disagreements, we discussed and we helped them to find a way out of the disagreement and to stay as a team and to find solutions. On the last day, we invited the students to CERN, and there was a presentation in front of a jury made of senior scientists and knowledge transfer experts. The jury was chaired by Frederick Bordry, who is the former head of Accelerators at CERN. And in order to decide in which order the teams would present, we made a quiz on the day before, and the teams that had the best answers choose when they would speak, and so on until we had the ranking to speak. And then each team presented its project and answered the question from the jury. And in the afternoon, there was an award ceremony with feedback from the jury for each team. So each team had to present its project from different point of view. Environmental science, what is the problem to be addressed? What is the solution? Accelerator, how to deliver the required beam. Physics, how to deliver the expected result. Engineering, how to make it fit. Legal, where we left open either to look at legal safety aspects or intellectual property aspects. Business, is it economically feasible? And communication, would such project be accepted by local communities? And it was very interesting to see how each team would address the problem and what they were bringing as solutions. So here I present very quickly the ideas that the teams had. So one of the teams proposed to strengthen the blades from wind turbines by irradiating them. So they found some data showing that when you irradiate polymers, they can become stronger, and that's what they were suggesting. Another team suggested to put a compact light source on a boat and to travel with that boat to oceanic gyres, where basically they would sample the ocean and look at water and microorganisms, and then also look at microplastics and toxic chemicals in the sea. A third team suggested to put an accelerator on a truck, and basically they would go to place where the soils are polluted, and by doing some treatment and some irradiation of the pollutant, they would be able to, they expected to be able to treat the soil and to clean it. And the winning team suggested to put an accelerator on a boat. And basically with that boat, they would irradiate, with that accelerator, they would irradiate algae bloom on lakes, and they would kill the algae while avoiding to kill the fish. And at the end, they were expecting to be able to kill to clean the lakes like this. And that's the team that was chosen as the winning team by the jury. Here you have a few pictures showing students during presentation. Here it's during the conference, and here it's after a seminar. They also had some time to rest, and I know that they worked very, very hard for the conferences. So that's after one of the two conferences where they were very tired. They also had some time to play. There was a visit at CERN, and I think for all of them, especially for the students who were not experts in accelerators, it was very interesting to have an idea of what is an accelerator. And they had some crazy idea about what to do with an accelerator. So now we are preparing the challenge 2023. We are keeping the same structures as in 2022, shifting by 1 day just because days of week are not exactly the same. So we'll get a virtual get-together on July 3rd, 2023, 4 online seminars and 8 or 9 in-person seminars, and we are still working on the program. One feedback from students is that they wanted more seminars at the beginning and more time to focus on the project at the end. So that's what I'm trying to do while preparing the program, and so far it's working more or less. This is a poster for this year. And the web page where you can find all the information, both just if you are curious about the project and also in case you want to apply, but our target audience is mostly master students. So the I.FAST CBI is a unique opportunity to study and work on accelerator application in a multidisciplinary environment. It's like what we do as accelerator professionals. Applications are welcome until February 28th. So far we have 50 applications. I think we'll reach about 100 applications, but we have very few applications from environmental science, law, and communication. We have more applications from physics and engineering, but if you have colleagues or students who might be interested, feel free to send them the link and to encourage them to apply. And we are looking forward to the I.FAST CBI 2020. Thank you.
Thank you very much, Nicolas. So that was very comprehensible and very compact. So thank you for this this presentation. And we have so if there are any specific question, and you recalled as well, and we will maybe send to everyone as well the link for applying. So that's you said next week already for the deadline.
So the current deadline is next Tuesday, 28th.
Okay.
So yes, if you know students who are interested, you should tell them to apply very quickly. Exactly. We are considering extending a bit the deadline for communication students and law students because we have very few applications, but it's not yet confirmed. So at the moment, if you know master student, tell them very quickly to apply.
Okay, so that falls very well as well, this timing for your presentation. So thanks a lot. So we'll make sure as well that the recording will be available so that we can disseminate as well in an effective way. So indeed, this multidisciplinarity is really the important aspect. And I think this was really the strength of the team that were working together, getting to know also what particle accelerators are, because maybe engineers and scientists would, but for communication and law, so that's a bit more difficult, although you need to have those 4 different disciplines to build up something that is very valuable. So this is why we will have the winning team now presenting so the perception as well of the school and as well a bit of the project. So Rema will represent the communication aspect of our project, but so we are looking very forward to understanding what her perception is and a bit more detail on what she had been presenting. So Rema, if you want to.
Thank you, Christine. So yes, I start sharing my screen. Okay, can you see my screen now?
Yeah, we can.
Okay, very good.
And in full screen.
Yes. Okay, so hello everyone. My name is Rima Tamimi. I am a master student in Science of Communication and Information at the French Press Institute in Paris 2 University. So currently I'm working for my thesis on science communication as a tool to challenge conspiracy theories around CERN. The idea was inspired by my short-term internship at CERN last summer. Mainly, I'm interested in the link between society and science, and its demonstration through media and public communication. So that's why semiotics and sociology are the main axes of my research. But today I'll be talking to you about my experience last summer in the I.FAST challenge-based innovation at the ASI, and what did this experience bring to me personally and professionally, let's say. It's interesting to look back on how my story began. I love telling stories. So last year in February 2022, someone to whom I'm so thankful sent me the I.FAST announcement. And at that time, I was so interested in the world of particle physics and engaged in the environmental issues at the time, but I had no knowledge about particle accelerators. Let's say I had scientific surroundings, but no knowledge about the topic. So this was an opportunity for me to jump right in the world of particle physics. So I applied and I received Nicolas' acceptation email in March. So let's say on 26th July, the beautiful 10-day story began at ESI. We were 23 students representing 17 nationalities, as Nicolas said. We were divided into 4 multidisciplinary groups. Mainly, we had 4 fields of studies, which were engineering, physics, environmental science, and social science, which can be communication, law, or business. So each team of us identified a specific environmental challenge, and then we proceeded to develop an innovative solution involving particle accelerators. So we had an intensive schedule, let's say. We had a series of seminars from leading accelerator specialists. So for me, it was my very first introduction to particle accelerators. It was so heavy, so heavy at the beginning, but yeah, day by day, I started understanding the basics and the goals. We also have a daily mentoring from different expertise like accelerators from Nicolas and others, and also we had communication assistants and communication advices, and I can say this point was the most useful for me. What I really liked about this this challenge is that even though it was challenge based or it was based on competition, but the program also had open innovation approach there. So all teams benefited from each other's experience. For example, we did not have a specialist in business in our team, so we consulted a member in another team and so on. And the members, a member from another team came to me to ask me about communication and body language in their speech. So we collaborate between each other to make the 4 ideas perfect, let's say, or as much as we can. So our team, as its name says, it's human beings. So we try to make our humanity the engine of our work. And I think this was the goal of the program at its all. We worked day and night, let's say. The day we had intensive seminars and we worked till the night. And the last 2 days we stayed up to 1 a.m., for example, to make a brainstorming together about our idea. But let's say what's really interesting about our idea is that, okay, let's explain what was our idea. So our idea, our project CERN, aimed to restore the cyan color of our lakes. And how was that? We targeted toxic algal bloom in the bodies of water in the lakes of France. So naturally, the green algae, in their natural states, they grow up in the bodies of water for several years. But recently, it's been proliferating, especially by the addition of nitrates spread by farmers in the fields. And these organisms can release very toxic gases. So what we propose to do is to treat lake surfaces using an electron accelerator. You can see it here. I think Nicolas already showed to you. So our proposition was to eradicate the algal population on the surface before the blooming period begins. What's really interesting for me in our project, far from the idea itself, was the backstage behind it. So before starting the technical details and the technical solutions, we did a very wide case study, let's say, until the time we decided to work on Brittany, the region of Brittany. So we in France. So we did a very wide case study. Each one of us with his specialty or field of study did a study on this region. For example, the lawyer with us studied all the facets of environmental law in France and also the legal regulations regarding the radiation, if you will use it in this area. And also the technical, let's say the engineer and the physics specialist also interested in the technical issues. For me, what I had to do is I was interested in the communication campaigns of this solution. So at first I had to present this case of study in Brittany for my team. For example, we studied all the media, the mainstream media about this problem, the media coverage. We also searched some social media groups about this problem and the activism behind it. We also read about the lifestyle of people in Brittany and how would they accept a solution like this in their community. So we had, let's say, a draft about this area, and we discussed it together before even going to the next step. So I think this part of our work was the most important, because we believe that finding a solution isn't the most difficult thing, but applying it is. So yes, our biggest concern was to get an integrated project. We had two main points or two main targets in our communication, which were public and decision makers. For public, we were interested, we designed two phases of our communication strategies. We had pre-treatment phase. In this phase, we listed communication materials that will be used with the public itself in the department of Côte d'Armor near the Lac Beaumeliac, and also treatment phase. Yes, the treatment phase. So these elements that you can see are we made a material for each one of them, and we included them in the report submitted for the jury. I put you an example. For example, we made this video to be displayed in the public spaces in the region, in the targeted region. It's a kind of sensibilization for them to know the danger of the toxic algal bloom for them, for their pets, and also for their children. We also designed some posters as we will really apply this solution in a month. So yeah, for the decision makers, our interest or our big interest was how to convince them that our solution is more economical than the traditional one. This was the first concern for us, for the decision makers. And then we intended really to convince them orally that it's easier for you, because decision makers love the easiest way. So we were also convincing them in this point, and our lawyer worked a lot about this side, about the legal sides, let's say. Now I will end with a personal impression, let's say. Of course, before the most important thing is that our idea won the preference of the jury at the end of the program. What is really interesting is that before starting the I.FAST, I had no experience in particle accelerators. I had the interest and the passion, but no knowledge. And it's really interesting how in 10 days I could present our idea in the main auditorium of CERN, where the Higgs boson was presented. So it's really very interesting for students to experience this. What I really want to say, to also talk about is that I really appreciated the system that we had about exchanging experiences. So in the I.FAST, everyone had its duties. We in science communication, what is really interesting is that we don't talk about an educational society talking with ignorant public. But no, we're talking about what lies these two words. So the I.FAST program, CBI program, really applied this to us. Like each one of us gave something to the other. The last thing I will really say is that I see that choosing a common goal for the program was so intelligent. Like despite our different nationalities, backgrounds, beliefs, or expertise, we came out for one thing to find an innovative solution for our planet. So it's one planet for everyone. Even so, I'm in communication, in a communication field of study or physics field of study. We have one interest. So I think this was the best thing about the engine of all of us. And that's it. Thank you so much.
Thank you so much, Rima. So inspiring. So it's really interesting how you can certainly then bring as well so new scientists or new people into communication to learn more about science. So thank you so much for conveying as well this positive message and how to save as well this environment, a common planet, as you said. And one of the points I really like what you mentioned about the integrated aspect, like, solution, we can find solution, but the implementation, this is the most difficult aspect. So that's the important part. So maybe for that, we had a question that Nicolas had answered in written, but maybe Nicolas, if you don't mind, because I think it's very related to that, is that how as well, so from this project, so coming at the I.FAST, the reality, the applicability of all of that, so how to bring reality as well. So then the next phase, that could be an interesting one, for instance, looking at, for instance, what Rima had presented. Is there any entrepreneurship or something beyond that could be thought of? So beyond the answer, or you can read the answer and maybe elaborate a little bit, if you don't mind.
Maybe just to comment, first of all, we have to be careful to separate I.FAST and the I.FAST CBI. I.FAST is a very large project with very real applications and so on. So that's why, I mean, in I.FAST, there are projects very, very close from reality. So, but for the I.FAST CBI, the students only had 10 days. So we cannot ask them in 10 days to check everything. For all the teams, what they did, they started from real research. So they went to look in the literature, and that was, I would say, more the job of the physicists, engineers, and environmental scientists to go to look in the literature for research papers about some possible applications. And then I would say what each team did was to think how to take that research and to put it in a context where it's useful for the environment. And what Rima has shown, for example, the idea to kill algae, there is real research looking how radiation can kill algae. So that's real work. Then the idea of how to put it on a boat and so on was discussed within the team. After the challenge, I tried to see if there was a way to do a follow-up for either for the winning team or for the 4 teams. The problem is that very quickly you need funding. And because it's a European project, it has been structured very early, and we did not find a solution within the project after the CBI 2022 for that. But that's something, I mean, I still have that in mind, and I think that would be very good if we manage to do it in the future. I don't know how far we will be able to bring the project, but what I wanted to do was to take them one step further. So check that it would be realistic, and then we would encourage them to do it on their own. But unfortunately, we did not have funding for that. And just making the student travel and so on, we would have needed some funding and some support that we did not have. I am trying again for 2023, we'll see. Otherwise, when we'll resubmit the application for the whole I.FAST project to the European Union, maybe we'll have a slightly different structure to have also a bit of money for after.
I think it's really important to look at from the program point of view, but I think one of the assets as well for this program is if now everything has been captured as well, there's this visibility for all those different ideas and program. And we have also Mina here with us who raised the question. And thank you so much, so Mina as well for those questions, because I feel that this is how from the beginning to the end, we could make as well a project concrete from the idea, the solution, and how to implement it. So do you agree with so what Nicolas had, and maybe from your case, so you could as well elaborate in terms of how you would think, because you are an expert in particle with the electron as well as the proton and the neutron. So maybe with Accelerator, you can give also your own insight.
Thank you very much for the nice talks and insights. And I personally become very inspired with all the I.FAST ideas and also this challenge while discussing with Christine about it. But yeah, I was thinking that whether is there any plans in I.FAST regarding to come up with a startup project or kind of an actually, yeah, these are some innovative ideas coming out of this challenge, and maybe other aspects of the I.FAST, or maybe some ideas that coming from the specialists in the field, but I don't know how they can be connected to this project and have their ideas, or maybe is there any support from this project in order to apply the idea and have the startup project?
So yeah, so regarding the I.FAST as a whole, yes, I mean the application and one of the duty of I.FAST as a whole, not the I.FAST CBI, is to interact with industry and to try to find how to transfer research to the industry. So there, yes. For the I.FAST CBI, also for the students project, we did not think about it when we were building the challenge. So when we were making the application basically to the European Union, which was 3 to 4 years ago now. So the funding has not been included to push one step further the project suggested by the students. I would say also, I was surprised by the quality of the project that came out of the students. It was of very good quality. And yes, I would have liked to take them one step further, but we did not include that in the application. So we did not have the funding. And then changing a project while it's, I mean, I.FAST is a very big project. You have 49 partners. So this means that when you make a change, you need to involve 49 legal departments, which it took a year to get it signed. And so basically, it's too late to really change the structuration of the project now. But in the future, when we'll reorganize the project, that will be the good time to make that suggestion and to try to organize it.
Mm-hmm. Thank you very much. But regarding the other parts of the I.FAST, because I was not sure that whether I missed it from the first of the presentation, or it was only based on CBI from the first. Is there any way that the specialists can connect to this project and develop ideas on applications of accelerators?
Yes, I mean, that's the goal of the I.FAST project. So for example, within I.FAST, there is one work package which is fully devoted to societal application of accelerators. So yes, and the specialists who invited last summer during the challenge, during the CBI, were mostly coming from I.FAST, and there are people who are really working on real applications of accelerators globally to society, some of them to the environment, some of them to other applications.
And then because I am not aware of that, so if I want to actually connect, how can I connect?
So the best is to go to the website, which is you type I.FAST CERN and you will find it.
Okay.
I think on any search engine, and then you will see the full structure of the project and who is working on what.
Perfect, thank you.
I see that Masoud has a question.
Question, yeah, but just to mention and to complement that, so I don't know if it's the same, but for MENA as well, ESS is involved, and we have as well the Infratech, for instance, this is a project, another grant connected, which could make as well, so using the feedback from this I.FAST, which could as well be very interesting and very connected. So it's about networking, it's about knowing what is existing, knowing how then to get also the concrete phase. And Nicolas, I think it's the important part, like for the next, because there's always like a 2 phase as well in every grant where for the next time, so you can as well see the evolution toward this entrepreneurship. And thanks a lot, Mina, for this question. It's very, very relevant and important. So sorry, Masoud. So I don't know if it was related to that. So this is why I took the opportunity.
Yeah, they are just really related to each other. I mean, I'm really impressed. I have to admit that really I'm impressed about the quality of the projects suggested by the students, very young students. And my question is that something that can be taken in consideration in the future is having a kind of mentor for his young students, because I mean they have the ideas, they have really very nice ideas, but they need someone with some expertise to guide them. So they have to do all the work, but they have to be just guided by some experts in the field that they choose. I mean that's my point.
So that's why when we invite people for seminars, we ask them to stay longer so that the students can discuss with them. Then, I mean, one of the big jobs when preparing the challenge, we spent a lot of time thinking what would be the best way to mentor the team. Initially, the initial plan was to have one mentor or even two mentors at some point per team. But then we realized that this person would become part of the team if he spends all his time with the team or if he's assigned to a team. And it might not be good in two ways. First, he might steer the team depending on his belief or his research or whatever. And that's not what we want. We really wanted to leave freedom to the teams. And same when we will be comparing the teams, are we comparing the mentors or are we comparing the teams? And that's why we decided to operate differently, where basically there was always one expert scientist, at least one expert scientist on site, except on Sunday. And I was going, or someone else was going to see the teams at least once a day, and we tried to go more often. They knew we were present, so they could come to discuss with us. But like this, sometimes I got the same question from different teams, and I try to give the same answer. There is no bias coming from the mentors. And I think, I mean, apparently from the feedback we got from the student, it worked rather well. I don't know how it would have worked the other way around if we had one mentor per team, but we discussed a lot, and that's what we decided to do, and I think it was okay.
Yeah, so thanks a lot. And indeed, maybe that's also like how to open gate for the future as well. So the database of the student and the potential mentor could be still available. So that's also for sure very important. So meaning that also for the case of now more environmental challenge. So maybe Masoud, you could explain a bit more as well what from your side at the Sesame, so you could foresee, or what does it mean for you? So how do you see the Sesame, so beamline, so addressing those environmental challenge?
Yeah, thank you very much. So I think from my personal place here, where I am dealing a little bit with some environmental research, scientific projects or topics, I would say that really when we say environmental science, it's really a very big and large word. And so it starts from air pollution to contamination, soil or water, it's nuclear waste storage, the ozone, and whatever. It's really very, very large domain, or a very a huge variation of domains. But anyway, when we see that people, I mean, when we talk about environment, is that how to preserve our planet, all what is inside the planet. So the ozone is the starting when we start from outside, going down to the air pollution. So what we inhale should not be really poisoned for us, for the plants, and for whatever is living on this planet. Going down to the food, and then contamination of the soils and water that we are drinking. So that's everything to preserve the humans and the planet. When I say then now on a global view, so it's fine how to solve this problem. But in any case, to know the problem, first we have to define the problem. What is it? I mean, we have a pollution somewhere. So how this pollution is coming? you have to find what is the problem. So when I talk, for example, about air pollution, this is a project that I worked with in collaboration with some colleagues from Egypt and Saudi Arabia. So we collected air. So what is the problem of the pollution in the air is particulate matter, is fine particulate matter, PM 2.5, that goes really deep into the lung. And if these PM 2.5 are really having them toxic or non-good elements like lead, arsenic, or chromium, copper in higher concentration, that makes really your life very complicated. First of all, you cannot inhale, so your lungs are done out. You cannot have a good respiration. Secondly, these elements are toxic and they can be cancerous. I mean, you can have a cancer just from there. You have a high dose of copper, you have a high dose of arsenic, you have a high dose of lead. So this is one point. So you have to understand what is the problem. In this case, so you have to find where is the source of this pollution. And by doing that, you have to know from where you have to collect the samples and how to treat them. So in order to go there, you have to find also a way how to look at this contamination. So to understand if this contamination is toxic or not, you have to know what are the elements. In this case, you can go to the synchrotron and you do different techniques. We have different techniques at Sesame, for example. We have the IR beamline, where you can look at the things that we have like molecules and so on. And you have also the XAFS XRF beamline, where you can, with the X-ray fluorescence technique, you can see what are the elements that are existing in this pollution. And also you can look at the structure itself. If, for example, chromium, you can see the oxidation state. If it's chromium 6, that is toxic and soluble and movable, or it is chromium 4, that is not toxic. Also for the arsenic or lead. This is one topic. So you have to know the problem, you define the problem, then you put a plan how to go with. Then you have to go more deep. I mean, I like the problem, for example, the project that was presented by the group of Rima Al-Tamimi. That's really a global view of it. But if why I ask this, the question for the mentor is if there is a mentor, we can go deep with this one and can look what is the structure inside, what is inside these parts that they are going to remove, and go deeply how we can treat them. Is it just possible with the different kinds? I mean, how can we do them, or how can we get use of them? Other problems of environmental problems also is soil contamination. So we all know that we have the fruits and vegetables from soil. And if we have contaminants in the soil, then that's going to be transferred to our bodies, to ourselves. And this is also a problem that you have to tackle. If you go to a soil, you don't know if you are working on a soil in any farm, for example, you don't know if it's contaminated or not, because you don't sense, you don't feel the contamination, you don't feel the arsenic, you don't feel the lead. For this one, you have to collect the samples, and you have to know what is in these samples in the soil by doing different techniques that exist somewhere outside in the lab or at the synchrotron. The most advanced is at the synchrotron, because there are techniques I can talk about that you can see. For example, if you go to the arsenic, the contamination is less than 30 ppm. Sometimes 30 ppm you don't see with other techniques, but if you go with the synchrotron X-ray fluorescence, you see it. And you know that you have a higher contamination with 35-40 ppm of arsenic. Then you have to look into the structure. Is this arsenic or chrome, is it toxic or not? Is it the part of it toxic? Because we have arsenic everywhere. But anyway, it's toxic in a given form. And the synchrotron, for example, if you apply the X-ray diffraction or X-ray absorption fine structure, you can look deep at the structure, and you can see how this element is, what is its form, what is in which form it is. So this is the part of most important one. So I think the students, they did a great job. They gave very global information about the problems. Then they need to go deep with this problem, and the synchrotron is there for that, and to go really to the deep part of the solving the problem. We have other applications into the environmental science. For example, nuclear waste storage or nuclear contaminations. Yeah, we have different nuclear reactors, and then you see that there are some in the environment. You have toxic or let's say elements that are not really very good. They can emit radiation. Therefore, I think we have to synchrotron is really the part, the large laboratory. I mean, I always say that it's a huge laboratory where you have different techniques that can help you to go in detail with the, let's say, faster, smaller, down to the atom level, to the electron level of the material. So
and do you have maybe some view, because I think that you had, if you could maybe so for the student, for instance, of the CBI, how a beamline would work, or the diversity as well.
So I'm gonna share just a few slides, and with this one I can show how we do that. I mean, I will start with this one here. So this is how it looks like, this huge laboratory. This is a synchrotron. The picture is from Soleil, and it has 3 accelerators. A LINAC, where you produce electrons, then you accelerate them into a booster, you boost them, and you accelerate them, the electrons, into the speed of light. They gain energies, and then they are stored in a storage ring. And then from there you have where you see different beamlines. All these beamlines, they are working together, so they receive photons at the same time, and it can be all used at the same time. So each beamline is has 3 or 4 parts. We have the front end, where it's connected into the this storage ring. We have the optics, and then we have the experimental station. So I just show here one beamline. This is a type of hard X-rays beamline. Most of the beamlines are really set like this. You have optics, different optics. Most important things are mirrors and monochromators to get a single wavelength or energy. And then you go to the experimental station. What is the most important there? I mean, this technique now is called the X-ray absorption fine structure and the X-ray fluorescence. We have detector for fluorescence here. We have detector counting the photons that are coming from the source. Then we will put a sample here. It will absorb the X-rays. Some X-rays are absorbed, and we have a reference. So the sample, when this photons are going to hit the sample, they will emit fluorescence, and with this detector we're gonna collect the fluorescence from each atom, and with this one we can know what are the elements, the atoms that are in our sample, and what is their concentration, how they are. I mean, if it's percentage or if it's just few ppms. And then with the other technique that is called EXAFS, we can apply a law that's called the D'Alembert law, and from there we can understand the structure inside. So this is how it is. The form of your sample doesn't really matter much, because we can use it as if it's a liquid, gas, or solid, powder, or just intact as a stone, or whatever you have in your sample. So also it can be plant, it can be tissue, whatever sample you have. And with this one, you can know exactly what is the concentration that you have for each element, it's toxic or dangerous elements. And also you can know how they are. If you know the structure, you can solve them. You can solve the problem. It's easier to solve the problem by knowing the structure. I mean, when I say that the structure is at the atomic level, how the atoms are set to each other. So I think, yeah, this is the last of it. I have many examples of environmental science, but I think if we have the questions, you can ask them directly, and they can answer them in different part of the environmental science.
Yeah, that's really interesting to see concretely as well the use of accelerator. So it's not directly accelerator like we know, so maybe with the LHC or with the ESS linear, but then with the Max 4 or all those capacity as well that that synchrotron can have. So thanks a lot for explaining how it works as well. And I think, Rema, so it's kind of an interesting way of seeing in that case, how then next the radiation as well could be as well used. And we can recall, and this is also a bit what Nicolas had mentioned for the soil, the treatment of the soil. There was as well a project where Accelerator could as well, so through radiation, find a way for protecting and cleaning the soil. So indeed, a lot of application with Accelerator. And you were mentioning indeed, so from the environmental aspect, and this is where it's really interesting that we have Jura with us. So you are working as well, looking at and observing the environment. So, but for more like at the higher level, if we looks not directly at the soil, but for the air. So any contamination of air as well that you could see through your measurement, and maybe the data aspect. I think it's an important way as well to better understand how we can preserve the nature. So what do you think? So from what was described by Ms. Soda, any complementarity with your research in terms of large scale as well research infrastructure in Sweden / Norway / Scandinavia?
All right, so I guess this is my turn to talk.
Yes, please.
Let me share my screen. I want to show a few slides. So this is something completely different. I'll promise you that. So I don't work with accelerators, although my dad was a nuclear physicist, and he worked with cyclotrons, and he worked with heavy isotopes. But I work with big radars and space physics. So I guess you can see a picture of a skier.
Yeah.
This is me. This is where I live. I live in northern Norway, which is 69 north. The reason why I live here is because we have this new interesting infrastructure project for monitoring the Earth's environment. These are my children, by the way. I have 4 boys. I bought them a drones, and I recommend buying a drone to your kids, because then they'll take pictures they'll take cool pictures with that drone. Yeah, I don't really have slides. I tried to very hastily put together some browser tabs to describe who I am, what I do. This is a picture of me. This is a picture of the types of infrastructure that I work with. This is the Arecibo Observatory radar in Puerto Rico. Unfortunately, it no longer exists, and because a couple of years ago it was destroyed. There was a hurricane, and the hurricane weakened the structure, and these cables, a couple of years later, these cables started snapping, and this whole thing came crashing down 100 meters, over 100 meters into the dish. But this is an example of the sort of infrastructure that I work with, and and what is this? It's a big radar that is pointed up. It's a big radio dish that is pointed up, and you can use this infrastructure for radio astronomy. You can also use it as a radar to study the Earth's ionized upper atmosphere. So anything above about 50 kilometers and up. All right, and what do we do with this, and why do we do this? So this is the Earth, this is where we are, and this is, from my point of view, this is the environment, right? We have the sun, which provides pretty much everything for us. It's the source of energy. The sun is not really just a light bulb. It's actually a big nuclear fusion reactor that provides light, and it also there's also a solar wind. You get this ionized plasma that flows outward from the sun, and it interacts with the Earth. And what we do with these big radars is we study space. We study the Earth's near space. What happens when the sun and the solar wind interacts with space. And here's another example of the sort of science. I took this figure from NASA. There's lots of different phenomena here that I don't think it's worth going through. The main one is ultraviolet radiation, which ionizes the upper atmosphere. And this is it's a global system, and you have different sorts of phenomena at different latitudes, and you have this red ring here. This is the auroral oval, and that's where most of the energy that's transported by the solar wind, and that interacts with the Earth's magnetic field. As you can see, the magnetic field lines here. Most of the energy for this interaction between the solar wind and the Earth's upper atmosphere, it actually happens here at high latitudes, and that's why we're building a big radar here, so that we can study what happens to when the solar wind couples with the Earth's ionized upper atmosphere. But there are numerous other different physical phenomena that we study. Ion neutral escape, for example, is quite interesting. Our atmosphere is not bounded. We're not living in a closed tank, right? The upper boundary of the Earth's atmosphere is space, and it's gravitationally bound to Earth. But there are processes which accelerate atmospheric ions, and can cause them also to even it can cause them to upflow, but even in some cases to escape the Earth. And that means that there's a loss process for the atmosphere to go into space. That's a very, very long-term process. Our Earth's atmosphere is not going to be lost in 10 years. We're talking about billions of years, scales of billions of years, where these things matter. But these are still very interesting phenomena to me. Here's another one. So why this matters to us? A lot of our infrastructure depends on space, because we are more and more reliant on satellites. So whenever you're navigating somewhere, you're using you're most likely going to be using GPS navigation, and GPS navigation relies on radio signals being transmitted between the satellite and you. And what happens? One of the reasons why it's important is because radio wave propagation is affected by plasma, by ionized atmosphere. The refractive index of radio waves is highly dependent on electron density, and this electron density changes because of this mostly solar inputs and the solar wind forcing. So you can have situations where you lose high precision navigation because you have some disturbances, some plasma turbulence in the upper atmosphere. Power lines, if you have a very dense patch of solar wind that interacts with the Earth, you can have large currents that flow in about 100-kilometer altitude. And whenever, Faraday's law tells you that if you have a large dB/dt, that can cause a large electric field, and that large electric field can induce currents into the power lines. Here's another effect. I mean, these northern lights you can see here. This is a phenomenon that occurs at the location where I am. So if you ever want to see the northern lights, which is this optical phenomena that occurs at high latitudes due to energetic particles raining down on the atmosphere, sort of a natural particle accelerator, actually. When the solar wind interacts with the Earth's magnetosphere, you occasionally get these situations where electrons are accelerated in the magnetosphere, and they come raining down on the Earth's upper atmosphere, and they collide with the neutral particles, and they excite them. And when that excitation is released, you get this emission of light. Yeah, I guess I won't talk more about that. There are numerous societal impacts by these environmental things that happen up in space. I think one of the environmental problems that is man-made that I have worked with is space debris. I don't have a slide of that, but our radars they measure Earth's ionized upper atmosphere, but they also measure little pieces of space debris. Our radar can measure a little coin, which is 300 kilometers away. And after over 50 years of space flight, we've sort of polluted space, and our space is full of small objects that are flying around there. And kinetic energy is half mv squared, and orbital objects are over 7 kilometers per second. Velocities, even small objects, can do a lot of damage to other satellites if there's a collision. I have another slide here. Here's one example that I thought of. I mean, how can we address environmental issues? So we all know that when you increase greenhouse gases, the temperatures tend to increase on the Earth. That's how the radiative balance works out, right? But what is much less known is that because this infrared radiation is trapped into the lower atmosphere, less of it gets to the upper atmosphere. So the upper atmosphere that I study actually cools down because of greenhouse gases, because of radiative transfer, and that's actually a really cool thing, because it provides another way to validate models of greenhouse gases and how they affect the Earth's atmosphere. There's a prediction that temperatures in the troposphere will increase, but there's also a prediction that temperatures in the upper atmosphere, in the thermosphere, above 100 kilometers, they will cool down. And this effect there is even larger, and it has been measured. These radars that I use, they measure the plasma parameters in the upper atmosphere, above 100 kilometers altitude. And here's a paper by a colleague of mine, Zhanran Zhang from MIT. He used close to 60 years of radar measurements, and he determined that sure enough, as predicted by, so he says, model predictions given by anthropogenic increase of greenhouse gases predicts that the thermosphere will cool down. But what he found was that actually it cools down even more. He's talking about 1 to 3 kelvins per year cooling in the thermosphere, and at an altitude of 270 kilometers. So it's another way to monitor what happens to the Earth's atmosphere. It's another way to validate that our models are correctly predicting what happens when you release greenhouse gases. And then for that, we need long-term monitoring of the Earth's upper atmosphere. Here are some nice pictures that I took from Tromsø. This is one of the radars that I'm using right now. This is the Tromsø ultra high frequency radar. It's a 930 megahertz radar with a 32-meter antenna. We transmit a megawatt of power up, and up in space we have the Earth's ionized upper atmosphere. And during this time, you can see this beautiful phenomena that we have at high latitudes called northern lights, or aurora borealis. And this is associated with particles that are accelerated in the magnetosphere that are raining down and causing impact ionization. You have these approximately 10 kilo electron volt electrons. Very low energies for you guys at CERN, but still large enough energies that you can see a visual phenomena. You excite the atmospheric, mostly the atmospheric oxygen, and then you cause this emission. Here's other pictures of these radars. when you send a radio signal to space, not much of it comes back. So that's why we need this big infrastructure. And what we're working on right now is something called iSCEA3D. This is iSCEA3D. This is a artistic rendition of the new radar that we're building. We're using brand new technology called phased array technology. And right now, this is what's happening right now. And so we are in the process of putting together this radar, and where the parts have finally arrived, and hopefully this year we'll be able to make first flight observations with our new ionospheric research radar. I think that's all I wanted to say. If you have any questions, I'd be more than happy to answer. And yeah, thank you for inviting me into this forum. It was a pleasure to talk a little bit about my science. And I'm sorry, I probably went over 10 minutes. Christina,
no problem. Yeah, because we wanted, indeed, one of the things we wanted to say is that we could have as well a longer presentation as well with all those nice view as well, les aurores boreales. So that was as well something really nice to show the aspect as well, the positiveness of how and why we need to protect this environment. And starting as well by the skier, I think it was super, especially for me, because I'm also the same type. So it's really important to see how we can really make the best by understanding, by measuring, by getting a good also instrument, like for instance, light source, and having a great student and the future as well for making as well for the next generation as well a better planet. So do we have a specific question? So maybe from Masoud as well, from Rema or Mina. So we will have certainly much more understanding as well of how it works I think we said sometime in July, so that we will have a full colloquium. So then indeed the time is turning, so we will then finish. And actually maybe yes, one question, because the next speaker will speak about gamma factory. And gamma, so there is the HACE, looking at the high energy stereoscopy system, so the one in Namibia. So it's quite an interesting as well research infrastructure for all those astrophysics aspects. So gamma factory, gamma production, the cosmos being as well an accelerator in that sense. So do you have any insight on that, Tejua? How the cosmos can be seen as an accelerator? I know you are not an accelerator scientist, or maybe because I know that Mina has a lot of great ideas. So would you think in terms of how to best understand this way of accelerating gamma? And then while I change the screen. It's a tricky question, I know. So no one there. So then I just then show you who will be potentially answering this question. So that's while sharing my screen, I will show you the next presentation, which will be about this gamma factory. And you see the same common denominator, the ski, the mountain. So Vitek Khanzi will present us how the CERN by itself as well, but how gamma factory could solve as well the different problems that we have on our planet. So gamma fabrication, we have the high energy gamma, I mean, from everywhere in the cosmos, and it's kind of an interesting way as well to go through. So there's going to be a presentation in March on the 23rd, also at 4 p.m. CET or 10 in America, so in Washington time. So you are more than welcome also to come and bring as well your questions on that. And I would like as well to take the opportunity to speak about the free session that the FIP, the Forum of International Physics, is organizing for the March meeting. So you will find much more information if you attend this meeting, which takes place in Las Vegas on the between the 5th and the 10th of March, so this year. And Rima, sorry, will so engage you further and will engage the young non-scientists in the world of particle accelerators, so through interdisciplinary youngs program. So she will elaborate a bit more on this CBI program. So it will be an interesting development that will fit with the forum of the early career scientists. So you might be the youngest, Rima, but I think it will be interesting to really, as this aspect of multidisciplinarity, to share it as well with physicists, because the March meeting is mainly condensed matter. There are a lot of quantum aspects, so you will learn certainly also much more. We have as well, so Mats Bertelsen, who will present so from the data aspect, so the DMSC and all the different simulation that will happen, so in connection as well with the ESS. And we have Munia Lassiri as well, so who is now working in Finland, but who is as well looking from the African side. She's from Morocco, but will explain the African strategy for the fundamental and applied physics. And much more speaker for that session, but I will pass also very quickly another session, so which will portray as well how diplomacy can be used as well, together with large-scale scientific facilities. So we will have so the former APS president describing, so in her role as well with the MagLab in Florida, how she portray and how she see all of this science diplomacy. And we have from Elise Rabinovici, who presented so last time, so this fabulous story. So he will now give a bit more of the tale of those two accelerators, meaning the LHC and the Sesame, so much more connection for the American public. And we will know also a bit more for the telescope, so also complementary from so what Juha was presenting. And we'll have so a third session where we will describe from the IUPAP, so which is the 100th anniversary. We had so last November, so a session as well for the physics matter, but this one will be complementary with different speakers. And we will find so Monica also summarizing how this event took place so last July. So in Trieste, so this was so the 100th year, and we had, so in November it was with Michel Spiros, who is as well representing the presidency as well of the International Year of so Basic Science and Sustainable Development. So that will be still at the end of that special year. So I think it will be a good way to finish that official UNESCO year, so with that session. And we will have also 2 award winners during that session, and it will be also so shared with the current president of the APS. So a lot of exciting time in perception, in view as well. So we will then look forward to meet you so soon. So from the aspect. So if we have further questions, we can otherwise now stop at the presentation. I see that so the mechanics we use for the gamma factory certainly exist in the universe and can explain a part of the observed gamma, the flux on the Earth. So an appetizer for his talk in 1 month. So thank you so much, Vitek, for this insight. So it will be then the lesson as well that we will hear next March. So thank you very much to everyone, and we will look forward then to see you in 1 month's time. Good luck for your research, and we will stay tuned. Thank you, everyone.